In the last video, we took a look at an example where it seemed that the curve that we were working with to connect the points 0, 1 to 1, 1 didn't really seem to matter thus far. And the question that we posed is, would it have made a difference at all, like for whatever curve we would have chosen, or would we have always have just gotten 1 back? Well, this brings up an important idea at this point about line integrals, and it's summarized in what we call the fundamental theorem of line integrals. Here's what it says. Let C be a smooth curve that's given by a vector function, where t ranges from a to b. Let f be a differentiable function of 2 or 3 variables whose gradient is continuous along that curve. Then, if I'm ever interested in integrating a line integral here, notice where I have gradient f dot dr, I automatically can see that this should be equal to f evaluated at the point determined by r of b minus f determined at the point, or evaluated at the point determined by r of a. This should be amazing. What this ultimately says is that if our vector field that we have sitting right here is a gradient vector field, meaning that I know the function I can gradient in order to get that vector field, so that means it's conservative, then all we would need to know is how to evaluate the endpoints within that function. So notice it's kind of like if I can do an anti-gradient of f and get back to here, I can just evaluate at b and evaluate at a, just first in the vector function, then in the original function f. So this is really, really crazy. We're actually going to go through here and try to at least give a super rough idea of where this concept comes from. And so we'll go through justification here if you're interested. So we'll prove not every possible case, but we'll prove in the case where r, our vector function, maybe has 3 components. So here's what we know. And I'll start with this. We know that if I was going to be working with something like a gradient.dr, I know automatically by stuff we have previously discussed that I could transform that into gradient of f, and I would just evaluate that at the components of r of t, and then dot that with r prime of t dt. Now, if I think about what all of that kind of represents, what that really means that I'm going to have is an integral from a to b, where I am going to have a partial of f with respect to x, a partial of f with respect to y, and a partial of f with respect to z. That's kind of my gradient. And I end up dotting that with the derivative of r, which would be derivative of x with respect to t, derivative of y with respect to t, and derivative of z with respect to t. And then, of course, a dt at the back. Now, if I was to actually perform this dot product, I could see that this turns into an integral from a to b of the following non-vector, but just regular old expression, where I'm going to have partial f with respect to x dx dt plus partial f with respect to y dyd plus partial of f with respect to z times dz dt, and then a dt on the very end. Now, if you look at this, you might actually notice that this right here looks very similar to a previous topic we've discussed this semester. Doesn't this kind of look like a chain rule? You might even be able to kind of guess what it's the chain rule of. So I'll say here that by the chain rule, we know that, again, if I was to write all of this back out, and I'll do it here quickly for the sake of clarity, that all of this resembles, again, a chain rule. But a chain rule of what? it seems to represent here a chain rule of an f of r of t, right? Because I'm taking the derivative of my function of f, which has components x, y, and z, but then I'm thinking about the fact that x, y, and z are in my r function, and those are totally determined by t. So the integral in this case becomes an integral from a to b of really just the derivative of my f of r of t dt, because I can just replace the chain rule. But of course then, that's really, really easy to then go ahead and just imagine how I would evaluate that. Because what's the antiderivative of the derivative of my function? Oh, well, that's just going to be f of r of t, and I would just have to kind of evaluate that from a to b. And so I get f of r of b minus f of r of a. And I have it. Now, there's a little bit of an abuse of notation that's going on here. Ultimately, again, we're thinking about this fr of t as a function which maps a real number t to some other real number. And so we can treat this like it's a regular Calc 1 function that we could use fundamental theorem of calculus on. So this is a really, really powerful idea. And one thing that's cool is we could even generalize that above argument to show that the result holds even if C is a piecewise smooth curve, which we've talked about before. In the next video, we'll take a look at an example of how we can actually use this to help us very, very quickly determine the work integral for a particular question.